few words about me. I'm a software and data engineering freelancer. If you want to contact me afterwards to discuss anything or just to keep up, you can go there. And first of all, why this talk? I mean, we all love new shiny things. A new problem occurs, we search the perfect solution, we look into new technologies we can use, and we, of course, most of the times want to search for the perfect solution. Also, we love complexity. Complexity is interesting. You can get lost in it. If something is simple, you're just done with it fast. And then, for example, if we need queuing, we think about Redis or RabbitMQ. If we need PubSub or events, we think about Kafka. And then we start to install the solutions. Okay. We start to install these solutions. Then we need to maintain them. And then at some point, maybe it sometimes feels as if the solutions maintain us because we get enslaved by them and we need to keep them up, we need to update them. And instead of solving real problems, we get lost in technology. We need to update our Kafka cluster, we need to update our libraries, we need to serve this. But what if we think about introducing, instead of the right tool, just the existing tool that we already have? Of course, every tool has its purpose, but also it has to be maintained, it has to be updated, you have to teach people how to use it. This all costs money and manpower. And most teams, they actually don't need Kafka or MongoDB, especially not small teams. Disclaimer, I like Kafka. I also see use cases in MongoDB, but not always. And keeping it simple and just making pragmatic choices instead of interesting ones is often useful. There are actually two talks or one talk and one article. They are pretty famous, maybe you know them. If not, you can check them out afterwards. There's the Boring Technology Club, which just makes statements, hey, use boring, which means establish technologies. And then there is also You Are Not Google, which goes into the direction, okay, these big solutions like Spark, they were developed by Google for their problem space. Then there was Kafka built by LinkedIn for their data volume and event volume. And just think a little bit more pragmatic. And still, if it turns out that you need the proper tools, you can still introduce them, right? So why Postgres? It's free. You don't have to pay for it. And also, it's free in the sense of it's open source. Postgres is continuously developed. It started in 1996. It still gets new features. And I think on GitHub, I checked a few days ago, it has about 62K commits. And I don't even know how many commits it has in total because, of course, Git was just developed at the beginning of 2000. So, yeah. Postgres has a lot of features, and it's also extensible. And maybe just to check how many, raise your hand, please, of you use or have used. Yeah, it's pretty much everyone. And so this makes, of course, my case with Postgres is just everywhere. It's one of the top 5 used database engines. You have used it, or at least by proxy, in some kind of product. And there are also client libraries for most of the languages that you can just use to do stuff with Postgres. And this brings us to how we can use the existing technology, Postgres, in our stack to tend to our new arising needs. We'll talk about publish and subscribe. We'll talk about distributed queues, document storage, and a bonus, if we have some time. You need to notify some kind of application from another application. For example, you inserted some rows, or you have some event that occurred in your system. Then this guy comes around and tries to sell to you. But you should consider Postgres notify listen. Basically, how it works is you have some database session 1 that runs a listen on the channel, and you have a second database session that has a notify with the same channel and some kind of payload. This results in the first session receiving the payload that the second session sent. Now I have a small demo, which makes it a little bit more complicated with the micro, but bear with me. So basically what we do is I'll just start a cluster and, or not a cluster, Postgres instance. And what we will see is that we have a listener and a notifier. And if we check the logs, this is hard now. Just let me set it up for a second. Then you will see that the notifier just sends some notifications and the listener actually gets them. So I put them next to each other and you can see, okay, the notifier just inserts some rows, it sends a notify, and then the listener receives the event. Thank you. I'll have to ask you a few more times to come up, unfortunately. Let's return. So basically you see, okay, we can pretty easily send and receive notifications. You can check the demos afterwards. I provide all the code. And you have to take a few things into consideration, actually. So every listening session is informed by every notify. So it's basically a broadcast. You don't have really a replay mechanism. So after something was sent as a notification, and if there is no instance listening, it's gone. So there is unfortunately no event replay like with Kafka. Then notifications are actually sent when the commit happens, but the listeners receive them on their session between transactions. So you have to do some kind of sleep and then check regularly. Instead of notify, you can actually use the PG notify function. And regarding the payload, it must be string, and it must be shorter than 8,000 bytes, so maybe some kind of ID or something that references something else. Notifications with the same payload within one transaction are only delivered once, but this also means you can notify multiple times within a database transaction. And sessions that listen to a channel, they can also unsubscribe. Something internal that you might stumble upon is there's an internal queue which just keeps all the notifications until the listening sessions receive them. The default size is 8 GB, and if the queue becomes full, transactions that call notify will fail at commit. You should consider listen notify if you have rather small events. You have small to mid data volume, so it's not suitable for really big data volume like Kafka, for example. If you don't need to reprocess missed events, and you don't need redundancy, because in the end, listen notify only really works on a primary Postgres server. Also, there's unfortunately no way to prohibit sessions from listening or notifying other sessions, so there's no authorization built in Postgres for this functionality. Distributed queues. So you want to decouple some kind of workflows, and you think about introducing some kind of distributed queue. Then you think about Redis or RabbitMQ to use, but also here Postgres comes to the rescue. You can use rather a long name, but select for update skipped logged. So how does it work? Basically, it grabs the rows that are returned by a query and then it logs them. But with this update skip locked, actually already locked rows are skipped. So you always receive the next unlocked row. Now we have a demo again. Sorry. And what we'll see is there's also Postgres set up, and now and we'll see that. Let me. Let me check one thing. And we'll see that there's a worker that's pushing just a few items in the table, and that there will be a few other workers that retrieve these items, and not yet. I'm still working on it. And let me just set it up quickly here. So what we'll see is now that we have worker 1 and worker 2. They basically query the same table, and now they just retrieve item after item. There are about 1,000 items in the table, and as you can see, they never process the same items because they basically acquire a lock on the row, and until they release the locked row, the other worker cannot really retrieve it. Let me just. Thank you. Now, a few more details. There is actually not only skip locked, but there is also that you can just select for update. This waits for locked rows, so this is really blocking code. Then you have select for update, no wait. If this query hits a locked row, then there's an error. But for our use case, we have select for update skip locked, which just ignores silently locked rows and keeps going and returns the next items in the table. In this case, it's really perfect for just concurrent processes that want to acquire rows, and they don't hinder each other. Yeah. Like I mentioned, you can use it to retrieve the next items. For this case, you always have to provide an order by that's deterministic. So if you, of course, use some order by that's not deterministic, you will always get different results, and then it's rather hard to retrieve the next item. You should always limit your result, because all the rows that you get a lock. So usually you limit to 1 to just get the next item, but of course, as mentioned at the bottom, you can also batch it. So you can, for example, limit to 5, and then you just get the next 5 unlocked rows. You also shouldn't hold too long the lock, because in the end, this will block the transaction. Also, this will block vacuum and just bloat your database. You could, for example, introduce an extra column that just tells you, okay, this row is at maximum locked until this time. And of course, you can use it, last point, in combination with notify listen, just to not poll the database the whole time, but just get a notification as soon as the next row is available. You should consider this if you want to concurrently process entries from a table or queue without taking care of the locking yourself. Of course, if you don't need persistency, you might also use an in-memory queue, but in this case, you can also just distribute it among processes on different servers. There's actually no proper way to really guarantee first in, first out, or some kind of fairness per key, or some sophisticated queue patterns. And this can actually run at quite a moderate scale, so thousands to tens of thousands of jobs per minute. But if you come to the millions, then it's rather hard. Document storage. You have some kind of data it varies in the structure. So of course, you might consider this guy. But of course, there's also a Postgres solution, JSONB. And JSONB is practically column type and allows you to store nested objects with varying fields. And the keys inside these values, they can just vary, but also they can be indexed and they can be used for proper selection and projection. Oh. Last time, I promise. So actually, it's not too interesting to see what's happening here. So I'll show you more the schema that's created. And I hope that's readable here in a second. So basically, you can then create some tables with JSONB, but you can also generate columns from the content. Then you can also add some constraints on the data itself, and you can also create, in the end, indices. And yeah, there is also, let me just show it. And then how it looks like is that there is, so basically some data inserted. Then you can see here the JSON structure, that's data retrieved from the JSONB columns. And here at the bottom, we see an explain plan, so the index inside this JSONB column, or which refers to a field inside this JSONB column works. And you can also do a lot of more stuff. For example, you can check, okay, is this key present? Is this value present? And you can even do partial indices on fields that have a certain value inside this JSONB stuff. Let's turn. Thank you. Of course, here you have also to pay attention to a few things. There are actually two types of columns in Postgres for JSON. I would rather recommend you to use JSONB because in the end it stores the data in a binary decomposed format. JSON really stores it in the text format that you provide, so you cannot index the data. Also, stuff like a white space is kept in it and not removed, and duplicate keys. The JSONB format, it removes also duplicate keys and allows you to use it for a lot bigger use cases. The JSONB operators, they provide you a lot of different functionalities. For example, you can check whether inside this JSON data there some keys exist. You can also even query nested objects inside this data. And there are different types of indices you should use. For example, if you really want to rather check is there a specific key in the data, the gene indices are rather recommended. But if you want to check for certain values on the keys, then I would recommend the default B-tree indices. And you can even use partial indices. So if a lot of rows don't have a certain key, you could still use that as an index to retrieve all the rows that have this key. You can implement check constraints, so you can make sure inside this data that certain values have a numeric type, that certain values, if they exist, they have some constraints. And you can, at some point, so even for the schemaless data, you can enforce some kind of format. Large JSONB values will be so-called toasted and compressed. But still there's a max size for one field, which is 1 GB, which is still quite large if you consider that MongoDB in the default setting, I think, has 16 MB per document. So, yeah. One thing you should keep in mind is that any updates on this JSONB data, even if you update only one field, generates a new row version. So this can, if you have a lot of updating values there, this can tend to get messy because then you need a lot of vacuums. So your table might get bloated after some time. And as mentioned previously, you can, from this JSONB data, just generate columns. So these column values will then be inserted if you insert your JSON data. You should think about using JSONB if you want to combine the advantages of a relational database with document storage. So you have a few regular columns that are present most of the time, and then you have JSONB for the varying data. And yeah, you should maybe think about not using it if you have a lot of updates to this JSON data. Small bonus. Vector storage, of course, interesting for everyone that wants to use RAGs. You need to store some vectors, you need to execute some operations on them, for example, nearest search or some calculations. And then, of course, you can look at some specific vector databases, but of course, you can also consider Postgres with a specific vector extension. How does it work? So these Postgres extensions, you can just download them and install, or just use some predefined images. For this example, I used Vector Court, which used to be PG Vector RS. They rebranded. There's also PG Vector, so there are quite a few. I have no affiliation with them. It's just the one I use. And basically, you can then just create tables and also query these tables with a column type that can contain vectors. I've also demoed there, but time, you can have a look at it yourself if you want to afterwards. What this extension does is it introduces the vector column type, but also a way to properly index this data. As you can imagine, maybe the default B tree is not the nicest way to use something like nearest search. And there are also operators that you can use the query for the data. There are actually a few different column types, so if you don't want to use too much space, and also a few different operators. There are, at least in a specific case of vector court, there are different operators recommended for the selection, so for the where clause and the ordering, but the documentation is quite good, and also this court is really helpful. They respond quite fast. The indices, they are also configurable depending on the vector size and the operators you need to use, and usually they recommend, if there are not like a lot of vectors, that you do the search by order bind limit, but you can also use where. But for that case, you need to use other operators, as I mentioned. You should think about using Postgres with a vector extension if you're just starting out with vectors, so you're not even sure whether you'll need it in the future. You want to keep them besides your relational data, and of course it will never replace a proper vector database, but you can still do that afterwards, right? And also the performance is quite good, at least of Vector Core. They also have some benchmarks up, so you can have a look on their webpage. Hidden bonus, a few more things you can use Postgres for. There's FTS, full text search, which wants to replace Elasticsearch. It's also a built-in feature. You can have a look in the official documentation. There's Postgres for geospatial data, and if you need to replicate and shard your Postgres, you can use the CTOS extension. And yeah, as you can see, we can get away with a lot less than we might think. But of course, if you come into the yeah, into the need of using the proper solution, you can still use it. These are my sources, and thank you.
This one is also working, yes. So thank you very much. If you have any questions, please put it in the Q&A. But so far there was none, so maybe any question in the audience? First one is the hardest one, yes.
Hi. Can you recommend, or what's your preferred way of interfacing with Postgres from Python? I think some of these patterns probably won't work with a traditional object relational mapper, so how do you do that?
Actually, in the examples, I used PsycopG2, but you still also can use it. You probably think about SQL Alchemy, right? You still can, it depends a little bit what you use in the background, but most of the times you can acquire the underlying connection and still issue these commands. So that's actually what we also did last year when we migrated in a project I was part of to SQL Alchemy. Then we still acquired the connection from underlying, and then we issued these statements directly on the connection. Yeah. Thank you.
Next question. Yes.
This update functionality, when something changes, that you want to be notified, etc. You said something, if it goes wrong, or if you use this functionality, that you should accept that it will not always work, or did I misunderstand it? Could you explain it a little bit?
What do you mean with it will not always? So there is no replay functionality. Maybe you mean this?
Yeah,
or?
that's the one.
Yeah, so I don't know where you're comfortable with Kafka, but there's these patterns about at least once, exactly once, at most once, etc. And this one is at most once because, of course, if you have no listener there currently, if you issue this statement, this notification is gone. Or if you're sending a producer, like in a Kafka context, issues the statement and the database connection breaks, it's also gone. So this is what I basically meant. So really in the worst cases, but I think these are also normal cases that you should consider if you interface with a Postgres database. Yeah. Thank you.
Another question? Yes. Doing my part also.
Thanks for the talk. So my question would be, do you have any experience how all of these facilities in Postgres compare in terms of performance? Not necessarily to Kafka, but maybe also to simpler things like Redis for PubSub?
I mean, of course, you don't have, Redis is relying, or Redis proposes the in-memory cache and also, yes, quite fast. For Notify Listen, I don't have really, I mean, it was quite instantaneous from my perspective, and probably still network is the biggest latency, because in the end, this is just a built-in feature of Postgres in C++, so it's still quite fast, and we used it to issue, really rather a lot of notifications, and they arrived within not seconds, but rather milliseconds. Yeah. And for the select for update skip locked, I think I mentioned that it's quite useful even for tens of thousands per minute. Yeah.
Thanks.
We have time for one last question. Yes, perfect.
Thanks for the talk. I wanted to ask, are there any special considerations needed for cloud-hosted solutions like RDS?
I think RDS supports actually also extensions, but you probably need to, if I think about the vector use case, then you probably need to introduce your own image. for the notify, listen, I mean, in the end, these are just normal database transactions for most of the stuff. So there's really no difference in whether you select or whether you just notify, listen. So if it's not if it's not turned off, but I cannot think of a way to turn it off. Yeah.
Okay, thank you very much. Please, a big round of applause.
Thank you.